Hello everyone and welcome to a presentation on time series analysis and forecasting of monthly airline passengers. In this project, we've analyzed historical airline passenger data using time series techniques like ARIMA and SARIMA with the goal of understanding the underlying patterns in the data and producing reliable forecasts. Over the next few minutes, we'll take you through our methodology, model selection, and the results we've obtained. The dataset we use consists of monthly airline passenger counts from January 1949 to December 1960, a total of 144 data points. Each point represents the number of passengers in a given month. As you'll notice, the series show a strong upward trend, seasonal repetition every 12 months, and increasing variance over time. These features make it a perfect candidate for time series modeling using techniques like ARIMA and SARIMA, which are designed to handle trend, seasonality, and changing variance. In this step, we visually inspected the time series to identify key characteristics. We observed that the series is non-stationary, both the mean and variance change over time. There's a strong upward trend, likely due to the rising demand of air travel and clear seasonality, as peaks occur regularly each year. The variance also increases over time, which is typical of growth data. Importantly, there were no structure breaks or intervention points. The pattern is smooth and consistent, making it ideal for forecasting after proper transformation. To prepare the series for modeling, we applied a log transformation to stabilize the variance. Then we used first order differencing to remove the trend and seasonal differencing at lag 12 to address the yearly cycle. After this, we examined the ACF and PACF plots. The ACF showed seasonal spikes and slow decay, suggesting a moving average component, while the PACF had a strong spike at lag 1, suggesting an autoregressive term. Based on these patterns, we specified the SARIMA model shown here, which captures both short-term and seasonal dependencies. Here we fit the SARIMA model to the log transform series using maximum likelihood estimation. The MA1 and seasonal MA1 coefficients were statistically significant, which confirms their relevance in the model. We evaluated model performance using AIC, PIC, and RMSE, all of which were low, indicating a strong fit. When we plotted the actual versus fitted values, the red line representing the model output closely followed the actual black line, confirming that the model successfully captured the data's trend and seasonality. To validate the model, we checked the residuals. The ACF and PACF of residuals showed no significant autocorrelation, meaning there's no leftover pattern in the errors. The histogram of residuals looked symmetric and roughly normal. And most importantly, the Lee-Jung box test returned a p-value of 0.6079, which is way greater than 0.05. This tells us that the residuals are independent. Together, these diagnostics confirm that the model assumptions were met and there were no overfitting of the data. To wrap up, our analysis began with identifying strong trend and seasonal components in the data. We applied log transformation and differencing to stabilize and stationarize the series. Based on ACF, PACF, and performance metrics, SARIMA model shown here was chosen and fit successfully. The model performed well and all diagnostic confirmed it was appropriate. Finally, the forecast plot shows that our model is capable of generating short-term predictions with well-defined confidence intervals, making it a useful tool for planning and resources allocation in airline operators. Thank you for your time.